But now that we learned events A union B, which is, or A or B, A and B, A intersect B, and then A complement or not A, now I want to find the probabilities of these events, of these new events here. That's our goal. I'm going to quickly show you the derivation of the formulas for these things, and then we'll practice with a couple of examples. And in this video, I'm just going to do the first one. So let's work on the formula for probability of A or E or B. Okay, so I want you to think about it like this. I want you to imagine that there's a person named, Amy. I'm using Amy because there's an A here. And there's another person named Ben for B. And these people are getting married. And A is Amy's wedding list. Okay, so in other words, Amy makes a list of all the people she wants to invite to her wedding, and that list is called A. And then Ben goes and separately makes a list of people he wants to invite to the wedding. So B is Ben's wedding list. So then what's A union B? Well, remember what union means or what OR means. You just take both lists and dump them into a longer list. So basically, this is the entire wedding list, all the people that are invited to the wedding. So everybody every person that Amy is inviting and every person that Ben's inviting is all on this one big master list. And now my question is, how many things are on this list? Okay, so real quick, let's say Amy is inviting, just to keep the number simple, 20 people. So Amy's inviting 20 people. So there's 20 people on her list. And Ben is inviting 10 people to the wedding. So now answer the question, how many people are invited total? Okay, if you said 30, you're right sometimes. Okay, as long as there's no overlap on these two lists, then you're right. Okay, there's 30. But if there's, like, for example, let's say Amy is inviting someone and then Ben is inviting the same person, then there's less than 30 because, you know, you're not going to send 2 invitations to the person. Or even if you do send 2 invitations to the person, that is only, so you're sending 2 invitations out, so you're sending 30 invitations out, but this one person is going to come instead of 2 people. Okay, so if the events are disjoint, okay, so that means there's nothing on both. So if A intersect B is empty, okay, that means there's nothing on both. Then you can just figure out how many people Amy is inviting to the wedding, how many people Ben is inviting to the wedding, and add them up. So you would get 20 plus 10, which is 30. Okay, so this is a formula, but this is only true if the events are disjoint, if there's nothing on both. So one more time, if you take 2 lists, one list has 20 things on it, the other list has 10 things on it, and you union them and you make one master list. How many things are on the master list? Well, it would be 30. You'd add how many are in each list as long as the events are disjoint, as long as there's no overlap in the events. Okay, so now that we wrote all that down, I'm going to just write it down again. Just a little bit neater here. So in the situation where the events have no overlap, okay, that means if you form the AND event, if you look at A and B, there's nothing on both lists. So you get an empty list. So in that case, then the number of things in A union B is equal to the number of things in A plus the number of things in B. Remember, this is not always true, but it's true if there's no overlap on the lists. And now what I'm going to do is I'm going to go ahead and divide every term by absolute value of S. I'm trying to derive a formula here, so let me go ahead and divide out by absolute value of S and see what happens. And now, okay, let me write down the equal sign and write down the plus sign. This term, well, what is that? We've seen that somewhere before. That was the probability of A. Remember when we talked about absolute values? Probability of A would have been absolute value of A over absolute value of S. Okay, can you tell me what this would be? Think about it for a couple seconds. And then you're going to realize that's the probability of B. Again, that's the formula we had for probability B, absolute value of B over absolute value of S. Now, can you figure out what this is? Notice it has absolute value of S in the bottom. What's the answer to this? If I were you, I'd pause the video for a couple of seconds, try to come up with it first before I tell you the answer. And now I'm going to tell you the answer. So the answer is probability of A union B. When you're trying to find the probability of something, you build a fraction. The top thing is whatever's in the parentheses here. So since the top thing is A union B, that's what's in the parentheses here. And there you have it. Then we have a formula for probability of A union B. So the probability of an OR, you just find the probability of each one and then add them. But that's only true if the events are disjoint. Okay, so that's one formula. So there's going to be a second one. Why? Because what if the events are not disjoint? Then we can't do what I did here. So the second situation is, what if the events are not disjoint? In other words, there's something on both lists. Well, then let's try to figure out what this is. So once again, let's pretend Amy is inviting, okay, number of people she's inviting to the wedding is 20. Number of people Ben is inviting to the wedding is 10. This is how many people are being invited total. But let's say that there's one person on both lists. Then how many people are actually invited to the wedding? Well, I'm sure you can figure that out really easily, and you can see that it's 29 people. One way of thinking about it, there's a lot of ways, but I want you to think about it this way, is you add the 20 and the 30, the 20 and the 10, you get 30. So it's like you sent 30 invitations out, but there's one person who got 2 invitations. So if you count the invitations, you haven't counted the wedding list. It's kind of like you take the person who got 2 invitations and take 1 away. So I want you to imagine it's like 20 plus 10. That's counting the invitations. If you want to count how many people you have, now you have to take 1 invitation away from the guy who got 2. So now you can think of the guy who got 2 as really just getting 1 invitation, and now you've counted the people. Okay, so it looks like it's 20 plus 10, and then you have to subtract 1 because one person got 2 invitations. Okay, let me change it. What if there's 2 people invited to 2 people on both lists? Then how many people total are invited to the wedding? Well, I'm sure you figured out it's 28. But think about it this way. If you just add the 20 and the 10 and you get 30, you've counted how many invitations you have, but then you've sent out too many because 2 people got 2 invitations. So imagine from each of those 2 people, you took one of the invitations away. So it means you're going to take 2 invitations away. And now you've counted how many people. So this counts the invitations, but now if you take away the extra invitations, you get how many people actually are going to the wedding. Okay, this is if there's 2 person, okay, people. 2 people on both lists. Okay, let's try it one more time. Let's say that there's 7 people on both lists. Then how many people are invited to the wedding? Well, again, you're not going to do 20 plus 10. Think about it for a second to see what the answer is. 7 people are on both, so you don't want to count those 7 people twice. So you probably came up with the answer 23, which is correct. But think about it in this weird way. That way it's going to help me get the formula that I need. Okay, so you start off by doing 20 plus 10. That counts the invitations. But then from the 7 people who got 2 invitations, you're going to take 1 away from each of them. So you're going to take away 7 invitations. If you take away those 7 invitations, now the number of invitations you sent out is equal to the number of people who are coming to the wedding. So you get 20 plus 10 minus 7. Okay, which is 23. But now in general, to generalize this, the number of people in the union event, number of people who are invited to the wedding total, what you do is you count how many people are on Amy's list, then you add to it the number of people that are on Ben's list, and then you have to take away a number for the extra invitations. Well, how many extra invitations? 7 in this case, because there's 7 on both. You have to count how many people are on both and take away that many. So if there's 7 on both, you take away 7. So how many people are on both? Well, that's this event, the ones that are on both, A and B. So the number of people on both, you take it away, and you get that. Okay, so when they are disjoint, you don't have this term. Okay, but if they're not disjoint, you have this extra term here. All right, so now what I'm going to do is I'm going to keep going to derive the formula the way we did in the disjoint case. Same thing, I'm going to divide everything by absolute value of s. If you divide this by absolute value of s, you get that. Divide that by absolute value of s. Divide that by absolute value of s. Divide that by absolute value of s. And this is probability of A or B. This term is probability of A. This term is probability of B minus, what's this last one? It's basically the probability of whatever you see up there. This is probability of A and B. And that's the second formula for the probability of an OR. So there's 2 formulas for the probability of an OR. It depends on if the events are disjoint or not. If the events are not disjoint, then it's this formula. And of course, if the events are disjoint, then you don't have this last term. Okay, I have on the next couple of slides, I have a summary of these formulas. So one more time, formulas for probability of A or B. It's called the addition rule because you saw there was an addition. There's actually a subtraction too, depending on if the events are disjoint or not. But either way, it's called the addition rule. Okay, so in the first situation, if A and B are disjoint, so if there's nothing on both lists, then the probability of A or B, what you do is you find the probability of the first one, then the probability of the second one, and then you add the answers. Again, that's why it's called the addition rule. Probability of the first, so when it's a probability of an OR, so when we're doing probability of an OR, it's the probability of the first plus the probability of the second, if the events are disjoint. So in other words, if you're going to use that formula, you need to first check to see if the events are disjoint. If the events are not disjoint, that means there's something on both lists, there's some kind of overlap between the lists, then the formula gets a little longer. Probability of A or B is equal to the probability of A plus probability of B minus probability of A and B. It's probably a little bit better to think about it this way. So if they're not disjoint and you're trying to find the probability of an OR, you do the probability of the first plus probability of the second, and then you have to minus the probability of A and B. It's got to be an and here. Okay, so we're going to do a couple of examples now in the video to practice these formulas, and then we'll do more in class. And then there's going to be some other things in the homework that we may not talk about. In general, though, how do you know which formula to use? So we're going to do some problems where even problems can be done multiple ways. When problems can be done multiple ways, you should know all the ways to do them. That way on an exam, you have some options, especially if you forget something, you're like, well, I know this way it will work, so that's nice. Other times problems are worded in such a way to where there's only one formula that will work. And then there's other problems in the homework you might see where they'll give you some parts of these and they'll ask you for the other ones. Usually you would use this formula if you're trying to find probability of an OR, and you just figure out what these things are and add and subtract them. But sometimes they'll give you a problem. You realize this formula is an equal sign, so technically they can ask you to find anything. So there could be a problem where they try to trick you, but they give you this, and they give you this, and they give you this, and they ask you to find that. Or, they can give you any 3 of them and ask you to find the 4th one. They can give you that, and that, and that, and you have to find that. Or in a disjoint case, usually, again, you'll have to find that, and they'll give you these 2 things. Okay, but sometimes maybe they'll give you this, and they'll give you this, and you'll have to find that. So anyway, there's lots of different kinds of things. Let's go. So the first part of what we're going to do today is we're going to practice finding probabilities of ORs. We're going to do a lot of practice because probabilities of ORs is probably the hardest of the 3. OR, and not. OR is probably the hardest one, so we want to work on that one. All right, here, let's see. So I'm going to give you a bunch of experiments, a bunch of events, and ask you to find some probabilities of ORs. So here we go. In this experiment, we're rolling a single die once. We have these events here. Okay, and look what it says. Find the probability of A or E, and then probability of B or D. So we have probabilities of ORs we got to find. All right. Now, sometimes when you do these problems, there's two ways to do it. And sometimes there's only one way that will work. So what I'm going to do is I'm going to show you both ways. And don't do it like this. I don't want you to be like, well, he's showing us two ways. I don't feel like learning two ways. I'm just going to pick the way I like and do it that way and ignore the other way. Don't do it like that, okay? And the reason is because depending on how the wording of the problem is, sometimes one way will work and not the other, whereas another time the other way will work and not the first way. So I need you to know both ways. If you get a problem where you can do it both ways, then you're free to pick the way you want. But know both ways, because in other problems, it might be one or the other that work and not both ways. Okay, so we'll call this solution one. Again, there's two ways to do this one. I want to go ahead and show you both of them. Solution one. In solution one, what I'm going to do is I'm not going to use the OR formula yet. You know, the OR formula I just showed you on the previous slide. We're going to do that for our second solution. This other way of doing this problem is to use the absolute value formula. I'm talking about this formula from, a week ago. Okay, this formula here. This formula can be used sometimes, and it can be used here. So I'm going to go ahead and use it here. So this solution is use the absolute value formula in the first step. This is what you do. So you put a fraction line. Whatever is in the parentheses needs to go on top with an absolute value. Now there's a bigger mess inside the parentheses, but you have to write the whole thing with an absolute value around it. Okay. Then on the bottom, let me erase this. I'll put it a little smaller. Well, here's solution one. Okay. And on the bottom, you're going to put absolute value of S. When you're using absolute value formula, you always put absolute value of S on the bottom. If you do it this way, it's a little bit shorter, okay, than the second way. But, so you might go, oh, I like shorter, okay. But the bad news is it's a little harder to count this way. So, one way is more writing but easier to count. One way is less writing but a little harder to count. Okay, so we got to count these things. Let's see, absolute value of S. Someone tell me what the absolute value of S is.
6.
6. There's 6 outcomes when you roll a die in here. I'll just remind you. Here's a sample space. These are all the outcomes when you roll one die. And I'm going to go ahead and write down what some of these events are. We wrote them down earlier, but let me just write them down again. A is even number 2, 4, 6. When I say earlier, I mean last week we wrote it down. B is, I might not need B. Let me just write what I need for now. So we need E. E is the die lands a number bigger than 2, so numbers bigger than 2 are 3, 4, 5, 6. Okay, so now we got to count A or E. So one way to do that is to figure out what A or E is. I want you to be careful when you're counting an OR. A lot of times people think you're supposed to add. There's 3 things in A. You can see over here, there's 3 things. There's 4 things in E. And remember what you're supposed to do, you're supposed to take these 2 lists and put them together. You might think there's 7 things total, and you might put the number 7 up here. This is totally wrong. Probability can't be 7 over 6. 7 over 6 is a number bigger than 1. Probabilities cannot be bigger than 1. So you do not add. Sometimes you add. You can count how many things are in here and count how many things in here and then add them. Sometimes, but not all the time. Basically, you can add when they're disjoint, but these events are not disjoint. So for this example, what I'm going to do is I'm just going to figure out what is this list. So again, you take everything from A, dump it on this list, take everything from E and dump it in this list, and make one long list. And when you make the long list, don't write anything more than once. So we've got to put 2, 3, 4, 5, 6, basically. Okay, so all these things go in there. So 2, 4, 6 is in there, 3, 4, 5, 6, all in there. And if you count how many things are in there, you see that there's 5 things. Okay, so the answer is 5 out of 6. Okay, that's one way to do it. Again, this 3 and 4, you don't have to write that or anything, but I'm showing you so you can see you don't just add how much is in each thing. Okay, so that's how that one goes. Okay, let me show you the second way of doing it. The second way of doing it is if you use the OR formula right at the beginning. Instead of using the absolute value formula at the beginning, use the OR formula. Now, if you can use the OR formula, there are 2 OR formulas. The one you use depends on if the events are disjoint. So you first need to figure out if the events are disjoint or not. So here's an event, here's another event, are they disjoint? Now, what I mentioned to you in the video was to figure out if they're disjoint, what you should do is you should ask the opposite question. The opposite question of disjoint is there something in both? So you guys tell me, is there something in both of these events? Yes or no?
Yes.
Yes, there's something in both. If the answer is yes to that question, then it's the opposite answer to if they're disjoint. So is there something in both? Yes, like the number 6. So are they disjoint? No. Okay, it's the opposite question. So what you're going to do is you're going to write down not disjoint above the parentheses there. Make sure you write that. I'm looking for that on the quiz. Okay, so not disjoint. Then if they're not disjoint, use the short OR formula or the longer one. Well, if they're not disjoint, you're supposed to use the longer one. The longer one goes like this. Probability of the first, which is A, plus probability of the second, which is E, okay, minus the probability of the first and the second. That's the longer OR formula. That's the one you use the longer one when they're not disjoint. Okay, then I will apply the absolute value formula. This is absolute value of A over absolute value of S. This next one is absolute value of E over absolute value of S. Bottom is always absolute value of S. The top is always whatever's in the parentheses with an absolute value. This one here, absolute value of S. And in the parentheses, you see absolute value of A and E. Okay. And so you see this is more steps. Okay, this one was just formula answer. Okay. But again, I do want to caution you on this one. If you do it this way, counting using this formula is in general not so easy. When you're counting over here, it's more things to count, but each one is easier to count. Okay, so let's go ahead and count some stuff. So here I have to count how many things are in A. Okay, so there's 3 things in A. 3 out of 6 total. This is saying, right here, it's saying count how many things are in E. Here's E, there's 4 things. So 4 things, 6 total. And then you got to minus something. So it says minus A and E. We never found A and E, so I guess I should find it somewhere. So let's put it over here. Now these events that I'm writing up on top, if you can do the problem without finding them, that's awesome. But if you need to list them, then go ahead and list them. Okay, so A and E. So here's A, here's E. I find A and E. Okay, I guess we need to talk about A and E. So you just list the things that are in both. This symbol means and. List the things that are in both. So take a look at list A, take a look at list E. Is there anything in both? You have to list everything that's in both. So what do I list here?
4 and 6.
4 and 6.
4 and 6, yeah. How many? And then it says count how many things are in there. How many things?
2.
2. And the bottom is 6. 2 over 6. And then you add and subtract these fractions. Now, if you're not good at adding and subtracting fractions, just type it in the calculator. Don't worry about it. But I'll just say something real quick here. If they all have the same denominator when you're adding and subtracting, then that's the denominator of the answer. And then, so you just copy down the denominators, and that's the denominator of the answer. Then to get the top, what you do is you just do 3 plus 4 minus 2. So 3 plus 4 is 7, minus 2 is 5. And you get 5 out of 6. Okay, so again, that's a longer way, but you're going to see in a problem we'll do in a minute. That way is definitely easier in certain situations, because counting an OR in general is not the easiest thing to do. But if you do it this other way, you didn't have to count an OR, you had to count an AND. And counting an AND is usually much easier than counting an OR. So I guess that's the main reason why solution 2 is better in some situations. Okay, any questions on this one? Okay, we're going to do another one on this example and then go on to the next example. So it says probability B or D. Let me just write this stuff down again. So sample space is 1, 2, 3, 4, 5, 6. Okay, and then B I'm going to write down, and D I'm going to write down, and B or D, oops, B or D will write down, and B and D will write down. Okay, B is the die lands on a multiple of 3. So the multiples of 3 are 3 and 6. D die lands on 4. Okay, now B or D, again, what does that mean? It means you take the list B and list D and dump them in one big list. Someone tell me what goes in list B or D. So it goes in here.
364.
364, yeah. I'm gonna write in order, but you don't have to. 364 is fine. Yeah. And while we're at it, let's find B and D. Okay, so and means list the things that are in both. What's in both?
Nothing.
Nothing, right? Okay. So if there's nothing on the list, then you write this symbol down. Nothing on both lists. Okay, so anyway, so we did that. But all that stuff up there is events. But now I'm going to find this probability over here. And again, there's two ways to do it. So one way to do it, solution one, is with absolute value formula. It goes like this. Absolute value formula, first step. Whatever's on top, whatever's in the parentheses, write it on top, put an absolute value around it. Bottom, absolute value of S. And then we count. Absolute value of B or D means count how many things are in B or D. How many things?
3.
3. So if you found B or D, then you just count how many things are in there and you're good. A lot of times finding this, though, it's so big that you don't want to find it, so we have to come up with other ways. We'll talk about it in other examples. Bottom absolute value of S, there's 6 things in S, and that's the end of the story for that way. Okay, so what I'm going to do now is I'm going to use the second solution is I'm going to use the OR formula to do this problem. Again, there's 2 OR formulas. The one I use depends on if the events are disjoint or not. So I need to know if they're disjoint or not. So to know if they're disjoint, I'm going to ask the opposite question. The opposite question of disjoint is there something in both? Here are the events. Is there something in both?
No.
No. So are they disjoint?
Yes.
Yes. Those are opposite questions. And we saw here, there's nothing in both. That's what that says. So they are disjoint. We're going to write the word disjoint above the parentheses. Okay, then we use the shorter OR formula when they're disjoint. The shorter OR formula says you do the probability of the first letter you see in the parentheses, plus probability of the second letter you see in the parentheses, and there's no minus term at the end. We're done with the OR formula. That's why I call it the shorter one. It doesn't have the minus term. Because they're disjoint, use the shorter one. And so now you're going to use the absolute value formula on this. This is absolute value of B over absolute value of S. This one is absolute value of D over absolute value of S. And now you count the things that it tells you to count. So the formula kind of tells you, okay, count this, whatever, and figure out the answer. Absolute value of B says count how many things are in B. You see there's 2 things there. 6 things in S. Same thing here, 6 things in S. And here it says absolute value of D, count how many things are in D. There's 1 thing in D. You just add these fractions. When you're done, 3 out of 6. And that's the end of the story on that one. So we do a lot more examples, but just remember, some problems can be done more than one way. Some problems can only be done one way. So in other words, this might be the only way that works. This way won't work. And in another problem, this way might be the only way that works. This way won't work. How do you know? Well, it totally depends on the information they give you in the problem. In this problem, we have all the information to do it either way. So let me say it one more time. Make sure you know how to do it both ways. And if you try this way and you get stuck, you go, oh wait, I don't know some of this stuff here. Then you try it this way and you go, oh, I'm able to do it that way, and then do it that way. Okay, so long story short, if a problem can be done more than one way, I don't care which way you do it, pick a way and do it that way. But if it can only be done one way, know both ways so you can find the way that will work. Okay, let's do more examples. Okay, another experiment. This experiment says, okay, so we're gonna draw a single card from a poker deck. We have all these events, and here it's asking me to find an event, and then it's asking me to find the probability of the event. Okay, here we go. So let's see. D are the kings, and E are the cards that have numbers on them less than 5. Let me write down D. D are the kings. So I have to list all the kings. Well, there's the king of clubs, king of diamonds, king of hearts, king of spades. Remember, there's 4 kings in a deck. So just list all the kings. That's D. E are the cards that have numbers on them less than 5. Remember that an ace doesn't have a number on it. King, jack, queen, those don't have numbers on them. So the number cards are the numbers 2 to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. But it's got to be less than 5. So 2, 3, 4 is all it is. So it's going to be 2 of clubs, 3 of clubs, 4 of clubs, 2 of diamonds, 3 of diamonds, 4 of diamonds, 2 of hearts, 3 of hearts, 4 of hearts. Run out of room. 2 of spades, 3 of spades, 4 of spades. That's E. But now it's asking us to find D or E. So we have to put them all together in one big list. So you just list them all together. So this is going to be king of clubs. So I'm just listing everything. King of clubs, king of diamonds, king of hearts, king of spades. Okay, and then the 2 of clubs. You just make the whole list. Most of the time, I don't ask you to make the list. I just say find the probability. And especially if it's a long list, you'd rather not make the list. But just so we understand how to make the list, I'm going to do it this once. 2 of spades, 3 of spades, 4 of spades. Just list everything in both lists and put them all together in one big list. So there's that. Okay, now let's do this probability of D or E. Again, there's two ways to do this. We'll call this solution 1. I think this is the last time I'm going to do it both ways, and then from now on, I'm just going to do every problem one way so we can save some time here. Okay, so the first way is if you use the absolute value formula right at the beginning. So it's going to be absolute value of whatever's in the parentheses, D or E. Bottom's absolute value of S, and now you start counting. Since I built the list D or E, you can just count it real quick. How many things are in D or E?
16.
Yeah, 16 is right. All right, so there's 16 things in there. And how many things are there in the sample space?
52.
52. There's 52 cards in the deck, and that's the end of the story, doing it that way. All right, let's do it the second way. And the second way was with the OR formula. Again, there's two OR formulas depending if the events are disjoint. I need to know if these events, this event, and this event are disjoint. So to figure that out, I'm going to ask the opposite question first. Is there something in both events, yes or no?
No.
No. Are they disjoint?
Yes.
Yeah, they're opposite questions. So if you say no, nothing in both, then yes, they're disjoint. And when they're disjoint, you can use the shorter OR formula, which goes like this: probability of the first plus probability of the second. Okay, put the first thing in the parentheses plus probably the second thing in the parentheses, no minus term. Only a minus term if they're not disjoint. And then use the absolute value formula. So this way it uses two formulas. You use the OR formula, then the absolute value formula. And then the formula tells you exactly what to count. This says count how many things are in D. If you look at D, there's 4 things, 52 things in the sample space. This says count how many things are in E. Here's E, and there's 3, 6, 9, 12 things there. 52 total. Add 16 over 52. Okay, that's example 4. Any questions on example 4? Okay, let's move on. Okay, so it's asking us to find a probability of an OR. Okay, once again, I'm going to show you two solutions. So, first solution, again, I want you to notice we're finding a probability of an OR. Okay, you see an OR symbol over here. Now, one way to do it is to use the absolute value formula right away. Then I don't even care what it says in the parentheses. Put that on top with an absolute value on it. On the bottom, absolute value of S. Then we start counting. All right, real quick. A stands, so we're playing roulette, okay? In this game, we're playing roulette. That means there's 38 things total because there's 38 slots total in a roulette game. Okay. Now on top, it's here we have A. Let's take a look at A. A are the odd slots. That means 1, 3, 5, 7, 9, so on. There's 18 odd slots. Okay, so 0 and 00 don't count for as even or odd. Let me go forward over here. If you were to play this game and you bet on odd, you would win if any number in here that's odd comes up. You don't win if either of these come up. If you were to bet on even, same thing. The number has to be from 1 to 36 and it has to be even. You might say, Greg, 0's even. And I'm going to say, well, yeah, in a math class, 0's even, but in roulette, 0's not even. In other words, if you play roulette and you bet on even, if 0 comes up, don't be surprised when they take your money. You lost, okay? So even means even number in here. Odd means odd number in there. But there's 36 numbers total in here. Half are even, half are odd. So there's 18 odd numbers. I'm just going to write that up here. There's 18 odd numbers. And then B is red slots. How many red slots are there? So besides the greens, there's 36 numbers. Half are red, half are black. So there's 18 red numbers. But let me just say this again. You don't add the numbers and put 36 here. This is a very common mistake, but that's the whole point of OR. You're not understanding an OR yet if you do that. I understand when you do an OR, you take a list and another list and put them together in one big list. So you might think you just add. But if there's overlap on these lists, then you don't add, okay? So even though there's 18 things in list A and 18 things in list B, that doesn't mean there's 36 things on list A or B. Okay, so it's not 36 that goes here. So we got to figure out what goes there. Now I'm going to do this in a very annoying way, but it also will illustrate the fact that counting an OR is not the easiest thing in the world. Okay, so what I'm going to do is I'm going to go one slot at a time, and you're going to tell me if we should count it or not. Okay, what are we trying to count? The things that are odd, so odd, or red. So remember that. We're counting. So if it's odd, you count it. If it's red, you count it. If it happens to be both, you're going to count it. but it's got to be odd or red to count it. Okay, so that's what or means. It has to be odd or red to count it. So let's go to this. Okay, so one slot at a time. Again, what are we counting? We're counting odd or red. Okay. Is this odd or red?
No.
No. Is this odd or red?
No.
No. Okay. Let's go to here. Is that odd or red?
Yes.
Yes. It happens to be odd, so we're going to count it. It's also red, but as long as it's one or the other, you count it. Okay, how about 2? Do we count 2?
No.
No. How about 3?
Yes.
Why?
Because it's odd and red.
Yeah, but it doesn't have to be odd and red, okay? As long as it's one or the other. Well, the fact that it's odd means we count it. Or just the fact that it's red. Because it's both even better. 4 we don't count because it's not odd, it's not red. 5 we count because it's odd, also because it's red. 6 we don't count. So I'm just going to go one slot at a time. 7, we count 7 because it's odd. We don't count 8. We count 9 because it's odd. That's 5 things so far. All right. Do we count 10?
No.
No. Do we count 11?
Yes.
No.
Yes. Yeah. See, 11 is where everyone gets stuck, right? But then you're going to learn now. It's odd. You got to count it. Okay. Count 11. It's odd. As long as it's odd or red. It's not red, but it's odd. As long as one or the other, you count. Is everybody following me?
Yes.
Yeah.
All right. Let's see. Let's go to 12. Do we count 12?
Yes.
Yes.
Yes, because it's red. It's not odd, but as long as it's one or the other, you count it. Let's go to 13. Do we count 13?
Yes.
Yes.
Yes, because it's odd. How about 14?
Yes.
Yes.
Because it's red. How about 15?
Yes.
Yes, because it's odd. Okay, cool. 16?
Yes.
Yes, because it's red. 17?
Yeah.
Yeah, because it's odd. 18?
Yeah.
Yeah, because it's red. 19?
Yes.
Yeah, because it's odd or red, either one. 20?
No.
No.
No. Okay, good. It's not odd. It's not red. Don't count. 21?
Yes.
Yes.
22?
No.
No.
Okay. Not odd. It's not red. Don't count it. How about 23?
Yes.
It happens to be both, but again, as long as it's one or the other, you count it. 24. Do we count that? Yes or no?
No.
No. Not odd. It's not red. 25?
Yes.
Yes. 26?
No.
No. Not odd. It's not red. 27?
Yes.
Yes. 28?
No.
No.
No. 29?
No.
Yes. Yes.
Yes. Just like 11 tricked you, 29 tricked you. Because it's odd. Again, it has to be odd or red to count it. Because it's odd, you count it. Okay, 30. Do we count it?
Yes.
Why?
Oh, it's red. It's red.
Red, as long as it's one or the other.
Yep.
31.
Yes.
Yeah.
Yes.
32.
No.
Okay, not again.
Oh wait, yes, it is because it's red.
It's red. That's right. Okay, good. 33.
Yes.
No.
The answer is yes. Why yes?
Because it's odd.
Because it's odd. That's right.
Okay.
Okay. 34.
Yes.
Yes, because it's
Red.
red.
It's red.
35.
Yes.
Yes, because it's
It's odd.
Odd.
36.
Yes.
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 Because it's
Red.
red. Okay. So I just went one slot at a time, and I asked you if I should count it. And if you, when we're done here, you see there's 26 things on this list. I didn't make the list, but the top number is 26. But again, if you were to add these, you would have thought it was 36 up on top. Okay, so just be careful on that. Okay, so the answer is 26. And hopefully this example illustrated to you that it's annoying sometimes to count an or. So doing it this first solution, even though the writing is less, this counting we had to go from here to here was, you know, it's annoying. It's a lot of work, and you got to be careful. Okay, and that'll bring us to our second way of doing it. So the second way of doing it is with the OR formula. The good news about the OR formula. So the bad news is it's more writing. The good news is you're counting easier things. Okay, so if I'm going to use one of the OR formulas, I have to decide if the events are disjoint or not. So I want to know if events A and B are disjoint or not. So odd, red, I want to know if they're just
They're not.
second way of doing it. So yeah, I need to know if these events are disjoint. The way to see if they're disjoint, you first ask yourself, is there something in both? Is there a slot that's odd and also red?
Yeah.
And like 1 is odd and also red, so there is something in both. So if the answer is yes, there's something in both, and the answer is that they're not disjoint. So yes to something in both, then no to disjoint. Okay, so they're not disjoint. Since they're not disjoint, you have to use the longer OR formula, which goes like this: probability of the first plus probability of the second minus probability of the first and the second. Okay, and then you can use absolute value formulas. Here you use absolute value formula in the first step. Here you use the OR formula, then use the absolute value formula on each part. This is absolute value of A over absolute value of S. This next term is absolute value of B over absolute value of S. And this is absolute value of A and B over absolute value of S. Again, it's more work this way, but it's easier things to count. The bottom is all 38 because they're all absolute value of S. Let me put that first. Okay, absolute value of A means count the odd slots. How many odd slots are there in a roulette wheel? How many odd?
18.
Yeah. This says count B, which is the red slots. How many red slots on a wheel?
18.
18. Let's see, if you were just to add those, you would have got 36, but the right answer was 26. The reason is because you counted away the stuff you shouldn't have counted, so you counted it correctly. So here I have to count an and, but just understand an OR list is usually a big list, and an and list is usually a small list. So we still have to figure out what's in there. I have to count how many things are both. So they have to be odd and red. I'm trying to count the things that are odd and red over here. Let me go forward to the picture. So we're counting the things that are odd and, not or, and red. Counting an and is easier than counting an or. And I'll just tell you which ones they are. These, well, you can't see that. Let me change color. Okay, so these are odd and red, those 5. So the reds are odd for a while. Then the reds become even. Then they're odd again over here. And the rest of the reds are even. So the ones I've circled are the ones that are odd and red. So how many are odd and red?
10.
How many of them? 10. Yeah. All right, so we go back to this problem and put a 10 here. That's how many things are odd and red. And then you add and subtract those fractions. I ran out of room and put the answer over here. And the answer, 26 out of 38. You do 18 plus 18, that's 36. Then you minus the 10, that gives you 26 out of 38. That's how that problem goes. Okay, questions? All right, let me see what this says. Okay, yeah, we got to do this one. Okay, here we go. Solution 1. Again, it's an OR, but I'm going to do it 2 ways. First, I'm going to do the absolute value formula way at the beginning. Let's see what this is. C is green slots. There's 2 green slots. I'm just going to put that there. There's 2 green slots. E is ball lands on a slot that's part of the first 12 bet. The first 12 bet is over here. So the first 12 numbers, basically. So what's on that bet? The first 12, these numbers. The numbers 1 through 12. First 12 numbers. So there's 12 numbers on that list. So there's 2 numbers on list C. Okay, so absolute value of C is 2. Absolute value of E, how many things are on E is 12. But how many things are on C or E? Do you add them and get 14? Remember I said you're not supposed to add them. But this time adding them is fine. Why? Because we have 2 things on this list, and there's 12 other things on this list. There's nothing on both. These are green. None of these are green. So we have 2 things, and we have 12 other things. So how many things total? 4. Or do you count each one individually and then add? Only if they're disjoint. If there's nothing in both, you can do that. But if there is something in both, then when you add, it's going to be too big. That's why you have to subtract something. That's solution 1. Any questions on that much? All right, let's do it the other way. So the second way of doing it is if I use the OR formula first. Instead of the absolute value formula, we do the OR formula first. So I have to know which OR formula to use. I have to know if the event is disjoint. So you first ask yourself, is there something in both? So you want to know if they're disjoint. You ask the opposite question first, is there something in both? Is there a slot on the roulette wheel that's both green and also part of the first 12 bet? Yes or no? So here are the first 12 numbers, and then here are the green numbers. Is there something that's in both of those lists?
No.
No. So are they disjoint? Yes. So they're disjoint. Nothing in both, then they're disjoint. And if they're disjoint, use the shorter OR formula, which goes like this. Probability of the first, no minus sign. So use the OR formula first, then use the absolute value formula. It goes like this. One for each term, and then you start counting things. Absolute value of C, we already found that. That's 2. C is the green slots. There's 2 green slots, 38 total. Here we're going to count the ones that are part of the first 12. There's 12 of those, 38 total. Add 14 over 38, and that's how that goes. Okay, that's example 5. Questions? Let's see, we have a couple more. Okay, so in this example, it says a blood bank catalogs the type of blood, including positive and negative Rh factor, given by donors during the last 5 days. So in the last 5 days, a bunch of people, it turns out 409 people, 409 people total gave blood. And we're writing down what type was it. Was it type O, A, B, or AB, type AB blood? And then was it positive or negative, meaning O positive, O negative, A positive, A negative. So we wrote down both those things, what blood type, and what was the Rh factor for the blood for each of the 409 people. And we get this table over here. The number of donors who gave blood, each type of blood is in the table, shown in the table. Okay, let me put a mark here. Okay, so every number in the middle of the table here is an and, okay? So like this 12, okay? It's in the AB column. This is the AB column. So 12 people had these 12 people had type AB blood, but also because the 12 is in this row, they also had positive Rh factor for their blood. So 12 people had type AB and also Rh positive blood. Okay, each number is an and, depending on what row and column it is. This number 28 over here, what does that mean? That means those people had type O blood and also Rh negative blood. That's what I'm saying. So it's an and. And then again, to get the totals, if you want to know how many people had type A total, you just go straight down to the total, 164. And what this is saying is, for type A, 139 had type A positive blood, and 25 had type A negative blood. But how many just had type A total? You add these, and they put the total down there. Okay. And if you want to find the totals for the positives and negatives, like how many people total who gave blood had Rh positive blood, you just go all the way like this, and you get the 344. So 344 people total had Rh positive blood. Each one of these all these people had Rh positive blood, but if you add them up, total amount of people that are Rh positive is 344. And then total amount of people that gave blood in that 5-day period is 409. That's what that is. That's a total, basically, all the numbers in the table. So I just want you to understand what the numbers in the table mean. And now it says a donor is selected at random. So we got 409 people, and we're going to select one of them at random. And then we have these questions. Take a look at part A. Find the probability the donor has type O or type A blood. What is the most important word in this question here? Most important word.
Or.
Or. Okay, it's an or question. So see, trying to find the probability of an or. Anyway, that's what we're talking about today, right? Probabilities of ORs. Same thing with part B. It says find the probability the donor has type B blood or Rh negative blood. Okay, so we're going to do this. Let's see. Part A, find the probability the donor has type O or type A blood. Okay, so here's part A, here's part B. Before I do any of them, here's the deal. Every problem we've done so far today, I gave you letters for the events. I said this letter, A stands for even, B stands for green, I don't know, whatever. And I made up letters for events. Now, it's very important you guys understand. If you get a word problem like this, and they don't give you letters for the events, then you have to make up letters for the events, and that's the first thing you need to write down. And I'm looking for this every time. So here's the deal. It says type O or type A blood. We need a letter for this. But we have a symbol for or, right? You know, this symbol for or. So basically, whatever's before the word before the word or, we need a symbol for that. And whatever's after the word, I need a symbol for that. Okay, same thing for this one. We have a symbol for or, but whatever's before it, whatever's after it, I need letters for events. So whenever you do problems like this, the very first thing you should write down is letters for the events. You can write something like this. So let O be the event. I'm using O for type O, but you can use any letter you want, but it makes sense. Use O for type O. That'll be the event that the donor, the selected donor, has type O blood. Okay. And then I need something for type A. I guess we'll just use A for that. Let A, and you don't have to write it over. It's the same kind of thing, right? Let A be the event the selected donor has. I'll just put type A blood. Then I need something for type B blood. So let B, we'll use B for type B. The event the donor has type B blood. Then we need something for Rh negative. So I'm just going to use N for negative, okay? Let N, but you can use any letter you want. Let N be the event that the selected donor has Rh negative. Okay, so every time it's a word problem, they don't give you letters for events. You need to make up letters for those events and write that at the beginning. Okay, now let's do part A. Find the part of the donor has type O or type A blood. So the next thing you have to do, so two things extra you have to do in this problem that you didn't have to do in the other ones. First, you make up letters for the events that are mentioned in the question. Then you got to write down the notation for the question. They're saying find the probability, so you're going to put a P, that the donor has type O or type A. So in here, we're going to put type O or type A. So you have to write that. This is the notation here for the question that's written in words. You're writing the math symbols for it. Okay, so you got to write this and you got to write this that were both done for you in the last few problems. But then once you do that, then it's going to look just like the last two problems. Okay, any questions so far? Okay, I'm going to just work on the OR formula. There's two OR formulas. The one I use depends on if the events are disjoint or not. So I need to know if they're disjoint. To know if they're disjoint, I'm going to ask the opposite question. Is there something in both? Can someone have type O and also type A blood? Is that possible?
No.
No, the answer is no. So are they disjoint?
Yes.
Yes. So I'm going to write the word disjoint on top. Let's always ask the opposite question first. Is there something in both? No. Are they disjoint? Yes. Because they're disjoint, use the shorter OR formula, which is the probability of the first plus the probability of the second. Now, I'm going to use the absolute value formula for that. It's going to be absolute value of O over absolute value of S plus, that's this plus here. The absolute value formula for that is going to be absolute value of A over absolute value of S. Okay, so we use the OR formula, then the absolute value formula, and now we do what the formula says. It says count how many people have type O. Let's go take a look. There's a table. Oh, sorry. Here. How many people have type O?
184.
That's right. Count all of them. So 184. Okay, so let's go forward. So that's 184 people have type O total. Over 409, there's 409 people total in the table. Let's go to this one. This says count how many people have type A. Let's go back to the table. Right here. Type A. How many people have type A total?
164.
There's 409 people total in the whole, you know, so that's the sample space. What was it? 164 over 409. Yeah. And then you add those and you get whatever you get. So 409 on the bottom, we got to do 184 plus 164. I'm getting 348. Is that right? 184 and 164. I'm going to check one more time. Yeah, 184, 164. Perfect. Okay. That's part A. Questions? Well, this part B. Part B says find the probability the donor has type B blood or Rh negative blood. Someone give me the notation for this one.
Probability of B union N.
Probability B union N. Find the probability, so that's that. Type B blood, that's that. Or that's that. RH negative, that's that one. So that's the notation. Okay. Again, it's an OR problem. There's two OR formulas depending on if the events are disjoint or not. So I need to know if they're disjoint. So I first ask if there's someone in both. Can someone have type B blood and also RH negative blood? Can you have both, type B and RH negative? Yes or no?
Yes.
Yes. And if you're not sure, let's look at the table. Was type B and RH negative, and you see in this problem, there's 8 people who have both. So there are people in both. Now, even though there's definitely people who have both, I only want to know among the 409 people if there's people in both. If the last 5 days, right, the people give blood in the last 5 days, if none of them had type B blood and RH negative blood, if there was a 0 here instead of an 8, then you could say they're disjoint. Because the sample space is just the 409 people that donated blood in the last 5 days. It's not everyone in the world, okay? But because there's an 8 here, there are people in both, so they are people in both, so they're not disjoint. Okay, so okay. So since the answer is yes, there are people in both, you're going to write that they are not disjoint. And because they're not disjoint, you're going to use the longer OR formula, which goes like this: probability of the first plus probability of the second minus probability first and the second. Then I'll use absolute value formula for all of these. Okay, and then you just start counting. I'll put the answers over here when we get them. Well, absolute S is 409, so all those are 409. Okay, we've got to count the people who have type B. Oh, we did that? No, we didn't. Okay, let's go back. Type B. How many people have type B blood total?
65.
How many?
Oh, wait. Let's look at negative. Oh, it's 45.
45. Type B total 45. Let's go forward here. So that's 45 there. Then I have to count the people who are RH negative. Let's go back to the table. RH negative. How many?
65.
All right.
65.
Then I have to count the people that are both, that are type B and RH negative. The and symbol's telling me how many people are both. Okay, how many people are type B and also RH negative? How many?
8.
8. Okay, 8. And then you add and subtract those, and looks like 102 divided by 409. That's how that problem goes. Any questions on that? So the reason I have this example going is because this is an example of a problem where the absolute value formula does not work. So it all depends on the information they give you. So here we go. Example 7. The probability the randomly selected person in the world will have brown eyes is 52%. The probability they have blue eyes is 18%. The probability they will have green eyes is 16%. The probability they will be left-handed is 10%. And the probability they will have blue eyes and be left-handed is 2%. Part A says, what's the probability the randomly selected person in the world will have brown eyes or green eyes? Again, the most important word here is, the word or. So they're asking us about an or. Part B, what's the probability the randomly selected person in the world will have blue eyes or be left-handed? Again, the question is about or. And part C, same thing. What's the probability the randomly selected person in the world will have brown eyes, blue eyes, or green eyes? So these are or problems. Okay, very first thing is I need to write down letters for events. So let's what do I need here? What's the probability the randomly selected person in the world will have brown eyes? We need something for brown eyes. We're not going to write the word or anywhere. We need something for green eyes. So I'm going to let B, actually I'm going to put BR, okay, because there's also blue eyes. So if I put B, you're not going to know am I talking about brown or blue, so I'll put BR for brown. Okay, let BR be the event that the selected person has brown eyes. Okay, And then we need something for green eyes. So I'll just use G for green eyes. Let G, again, make sure that if I don't give letters to you for an event, you write them down for me at the very beginning. Let G be the event that the selected person has green eyes. Let me move forward so I can see what else we need. We need blue eyes and left-handed. Okay, I'll write it here. Let BL be the event that the selected person has blue eyes. And then we need left-handed, so I'll just use L for left-handed. Let L be the event that the selected person is left-handed. I think that's all we're going to need because in part C, it just uses the same stuff again. Brown eyes, blue eyes, green eyes. We already have letters for those. Okay, let's go back to part A. What's the probability that the person in the world will have brown eyes or green eyes? We have to write the notation now. Someone tell me the notation for this problem. So probability what?
BR or G.
Right, so just like that. You can write the word or instead of this if you want, it's up to you. But yeah, so again, 2 extra things you have to do in this problem that you didn't have to do in the first 5 examples. Write down letters for events if I don't write them for you. And write down the notation, the mathematical notation for the question if it's written in words instead of in notation. Now, we're going to just go ahead and use the OR formula. There's 2 OR formulas depending on if the events are disjoint. So I need to know if these events are disjoint. So I want to know if there's somebody in both. Can someone in the world have brown eyes or green eyes? Now, let me stop you real quick. You might say, hey, I know someone who has brown eyes and also green eyes. Okay, I know you might say that, but we're going to pretend that that doesn't exist. Okay, so I know that's a little weird, but just pretend that no one in the world can have brown eyes and also green eyes. So if no one is in both lists, then these lists are disjoint. Because they're disjoint, use the short OR formula or the long OR formula?
Short.
Short one. It's probably the first plus probably the second. Now, check this out, guys. Do not do this. I know in all the other problems I did this. This time, don't do this. Why? Because if you do this, I don't know what these things are. How many things are in the sample space? The sample space is all the people in the world. How many people are in the world? Yeah, I know it's like 7 billion, but they don't give it to us. I don't know how many people have green eyes. I don't know these numbers. Do you understand? So don't use the absolute value formula if you're not going to be able to count those things, if you're not given those things. But the good thing about this problem is it's less work than that, because once you've written this, this is the probability a person in the world will have brown eyes. It's given to us. It's 53%. Just put in the answer, 53%. This is the probability a person has green eyes. It's 16%. Just put that in there. And then you add. So the way this problem was worded, writing absolute values will not help you. But actually just using the OR formula, just the one step of the OR formula, now you can fill in all the numbers and get the answer. The answer to this is 69%. And we're done with part A. Any questions on part A? All right, part B. What's the probability that person in the world will have blue eyes or be left-handed? The notation, someone tell me the notation, please. So you have to put the P outside because I'm asking for a probability. Inside, you gotta communicate to me blue eyes or left-handed. How do I write that?
GL or L.
BL or L. Yeah. Now I want to know if they're disjoint, so I know which formula to use. So I need to know if something's in both. Can someone have blue eyes and also be left-handed?
Yes.
Yes. So are they disjoint?
No.
No, not disjoint. When they're not disjoint, use the longer OR formula. It's going to be probability the first plus probability the second minus probability first and the second. And again, from here, we know all the answers to these 3 probabilities are given in the problem. So just put the answer in there and be done with it. Probably person has blue eyes is right here, 18%. The probability person's left-handed is 10%. The probability person has blue eyes and is left-handed, that's here, 2%. So it's easier. You know, you just fill in the answers. 18 plus 10, 28 minus 2, 26%. Okay, that's part B. Any questions on part B? All right, last one, part C. What's the probability random selected person will have brown eyes, blue eyes, or green eyes? All right, so I guess there's a couple things to say here, but in math notation, you can't put you're not going to put a comma between events. The only thing you can put between events so far is this or this. So you have to rephrase this question because there's 3 events. There's brown eyes, blue eyes, or green eyes. The word or is there once, but we have to rephrase it. It's a small rephrasing, but next class is going to become more important where we have to rephrase the question. So we got to rephrase it and we have to say, what's probably the person has brown eyes or blue eyes or green eyes? So the notation is going to be brown eyes or blue eyes or green eyes. I mean, it's not a big deal what I'm saying, but the point is in the problem, you only see the word or once, but you wrote the symbol or twice because between events, you have to have some kind of symbol. You're not going to write brown eyes, comma, because they put a comma here. Okay, so that's the notation. Now, we never saw an or with 3 events in here, but there's 2 or formulas, right? Depending on if the events are disjoint or not. So those formulas that I gave you for or for 2 events can be extended to finding probabilities of ORs when there's more than 2 events. But the not disjoint one is very complicated. I mean, it's complicated enough to where I'm not going to go over it in class. But if these events are disjoint, so when they are disjoint, you can extend the formula real easily. Let me back up. How do we know they're disjoint? What does it mean for 3 events to be disjoint? It means any 2 of them are disjoint. So let me ask you this. Let's pick these 2. Can somebody have brown eyes and also blue eyes? No. Are they disjoint? Yes, those 2 are disjoint. Now you have to go to this pair. Are they disjoint? So can someone in the world have brown eyes and also green eyes? No. Are they disjoint? Yes. Then you go to this pair. So when you have 3 events, you have to look at all pairs and make sure they're all disjoint for me to say that it's disjoint. Can someone in the world have blue eyes and also green eyes? No. So are they disjoint? Yes. So they're disjoint. What does the disjoint or formula say? You do the probability of the first plus probability of the second, but now we have 3 events. So what do you think it's going to be? Probability of the first plus probability of the second. What do you think?
Plus the third one.
Plus probability of the third, yeah. So you're just extending that OR formula to 3 events. And then I'm going to put these answers in here. This is 53%. Blue is 18%. Green is 16%. Yeah, and you just add those. 53, 71, 81, 87. And that is the end of the story on example 7, and that's the end of the story on OR problems. Okay, so we're going to move on to another topic. So I'm pretty much done covering probabilities of ORs now, okay? But they're not easy, okay? So make sure you practice them a lot, especially the word problems, okay? So practice those a lot. But now we're going to talk about something else called conditional probability. We found probabilities of ORs. My next goal is to find, how do you find the probability of AND, okay? But in order to do that, we have to learn this other thing first called conditional probability. Okay, so in a conditional probability, basically the idea is, you know, you calculate a probability and then someone says, wait, I have new information for you. And then you recalculate the probability after you've been given new information. That's what a conditional probability is. Let's take a look at this first example here. So I usually give a story and I say something like, you know, I sell everything, I took my life savings and, or, you know, or whatever, and I went to Vegas and I was going to bet it all on red, okay? So the story is I go to Vegas, I take $10,000, I sell everything I have and I end up with $10,000 and I take it to Vegas and I'm going to bet the whole thing on red, okay? And I go with a friend. This is a fake story, but just go with me on the story. So I go with a friend. Now I get there and I bet the whole $10,000 on red. Okay, what's the probability that I will win? if I bet 10,000 on red, what's the probability I'll win?
18 out of 38.
18 out of 38. There's 18 red slots, 38 total. Did I write that down over here? So probably I win is, yeah, probably that I win 18. Here, let me write down. Probably I win is a probability that it lands on red. So yeah, 18 out of 38. Okay, but then, so let me tell you about the friend that I went with. Okay, so the guy I go with, you've heard of poker face. This guy doesn't have a poker face. He has a poker voice. He speaks very monotone, and you can never tell if he's happy, sad, never tell any emotion by just listening to him talk. So I bet the $10,000 on red. Now I tell the dealer, spin the wheel, hurry. So before I change my mind. Then he spins the wheel, the ball is spinning, and now I'm freaking out. Oh my God, everything I have is on red, okay? So I can't take it. So I step a little bit away from the table and I cover my eyes. I can't watch. And then I hear the ball lands. It's landed in a slot. The game is over. I either won or lost, okay? And I know I have an 18 out of 38, which is, just so you know, about 47%. I have 47% chance of winning. But then when it's over, my friend makes the following comment. He says, he doesn't tell me if I won or lost. Here's what he says. He says, well, it didn't land on green. That's what he says. He just lets me know it didn't land on green. But the point is, with that information, what he's basically done is he's eliminated the greens as possible. Imagine on the wheel, they've kind of been eliminated, those two green slots. So here's the idea. Conditional probability, you're given information. What that information does is it changes the sample space. Before I was given the information, the sample space, like what are the possible outcomes, any of the 38 slots on the wheel. But after I'm giving that new information, it's kind of like it eliminates some of those as being possible. So sample space changes. That's the most important thing I can tell you about conditional probabilities. Sample space changes. So here's the new information. It didn't land on green. Now the question is, what's the probability that I win? The probability I win now,
50.
yeah, it's 50% because it's 18 red out of 36 now. Why 36? Because once you said it's not green, pretend they're not even possible. This is what's on the wheel, and yeah, 50%. That's a conditional probability. Okay, it's after you've been given new information, it's going to change the sample space, and you can recalculate the probability. Let me give you another example. These are two usually preliminary examples I give in class. So here we go. This example, I usually say somebody in the class committed murder. Okay, so someone in the class. Let's say there's 40 students in the class, they're men and women, and somebody committed murder. It is known that someone in the room committed murder. Okay, what's the probability the murder is female? Probability murder is female. Well, as of right now, if all I know is that the murderer is somewhere in the class, it could be anybody, so you can go and count them, and there's 40 people total, and you count the females, let's see, 4, 3, 6, 2, 5, looks like 20 females, so it looks like I have half and half here. So the probability the murder is female right now is 50%. If all I know is it's somebody in the class, let me make this a little bit smaller. Okay. And then what's going to happen is we're going to be given new information. So I want you to imagine now a murder investigator comes, interviews everybody in the room, does his research, and he figures out, let's see what it says here, new information. After further investigation, it is determined the murderer is in the first row, meaning the murderer is here now. Okay? Just by that information, knowing that the murder is in that row, all these people have been eliminated as being possible suspects. So sample space changed from everybody in the classroom to just the people in the row. Get that idea, that's very important. The sample space changes. Okay, so now I can ask you, what's the probability the murderer is female? Prime murder. What's the bottom number now? Just the bottom number.
4.
4, yeah. It went from 40 people to just 4, and there's only one female in that row, so now the probability the murder is female is 25%. That's a conditional probability. It's like you're updating a probability after you've been giving new information. Okay, let's move on. So, some symbols and stuff, and then we'll do another example. So it says let A and B be two events. The notation for conditional probability looks like this. So you're still going to have a P, you're still going to have parentheses. But inside the parentheses, there's going to be a vertical line. And one event is going to go here, the other event's going to go here. The event that you put here is the one you're finding the probability of. And the event that you put here is the new information you're given. And you read this line as given. So it says probability, this mess, you read it as probability of A given B. It's the probability of event A. We're trying to find the probability of the first one, given that event B has occurred. So B is like the new information. The one we're finding the probability of is on the left. The one on the right is like the new information. So B has occurred. Find the probability of A. Some notes. First of all, when you're finding probability of A given B, okay, A is the event you're finding the probability of given the new information B has occurred. So again, the one that's on the left side of the vertical line, that's the event you're finding the probability of. This represents the new information. When calculating probability of A given B, the sample space changes. So that's the most important thing I could tell you about conditional probabilities. The sample space changes. Sometimes students will ask me if this event here after the vertical line is the new sample space. And my answer is sometimes it is, sometimes it isn't. So all I can tell you so that I'm not lying to you is B helps you figure out the new sample space. Okay, sometimes it is the new sample space, sometimes it's not. This says probability A given B is usually not the same as probability B given A. When you're finding conditional probabilities, make sure, especially if you have to write the notation on your own, make sure you get the order correct, because if you switch the order, the meaning is totally different and the answer most of the time is different. Sometimes it's the same, most times it's different. Okay, then we have this word independent. This word really confuses people. So I'll try to explain it the best I can, but focus really hard on this one. Events are independent, A and B are independent if the probability of A given B is equal to the probability of A. You know we had this word disjoint earlier, or last class I taught you the word disjoint, or whatever, the video from last class I taught you this word disjoint. Disjoint is really easy to understand. Is there something in both? Yes. Then are they disjoint? No, it's opposite. Nothing in both, they're disjoint. That's what disjoint means. Independent, on the other hand, is really hard to understand because the definition of it is very mathematical. So if I give you two events and I say, are they independent? There's no way out. The only way you can figure it out is you have to calculate two probabilities. One of them is going to be a conditional probability. One of them is going to be a regular probability. And you need to check and see if they're equal or not. If you get the same answer, then they're independent. If you get different answers, then they're not independent. And the story is over. If you go, Greg, but I still don't get what independent means, there's really nothing further to tell you. I mean, there is a little bit, but it's basically if these two answers are the same answer, then they're independent. If they're different answers, they're non-independent. Let me say it again. When you're trying to figure out if two events are independent, you're going to calculate a conditional probability and a regular probability and see if they're equal or not. If they're equal, so if they're equal, they're independent. If they're not equal, they're not independent. And the story is over. Okay, now that I said story is over, I'm going to say some more things. One thing to understand is this is a conditional probability, this is a regular probability, but whatever on the conditional probability side, whatever's before the left, whatever's on the left of the vertical line must match what's in the parentheses there. So let me give you a different example. Let's say we have two events, one of them is R and one of them is T, and one of these events are independent. Well, what you're going to do is you're going to write a conditional probability and a regular probability. I'm just leaving space for now. Okay. You put one of these here, the other one here. I don't care where you put them. Let's say you decide to put the R here and then the T here. But once you've decided what to put on the conditional probability side, then you're not free to put anyone you want here. You must make sure the one in the parentheses here matches the one that's on the left side there. So you'd have to calculate probability of R given T and calculate if that's equal to probability of R or not. If they are equal, they're independent. If they're not equal, not independent. If you decide to put the T here and the R here, then what has to go here?
T.
The T has to go here. Again, this has to match what's on the left of the vertical line. And then you calculate those two things and see if they're equal, and that's the end of the story. Now, there's one situation, only one situation, where you're going to know if the events are independent right away without doing a calculation. And that's if you're doing a problem involving drawing more than once. It says if you're doing problems involving multiple draws, drawing more than once, if you draw with replacement, then every draw is independent of the others. If you're drawing with replacement, that means you draw, you put it back, you draw, and then draw again. If you're drawing without replacement, then they're most likely not independent. So that's the only time you know if they're independent. Oops, where'd it go? Okay, so if you're drawing more than once with replacement, then every draw is independent of every other draw. Otherwise, you don't know. Okay. All right, we should do some examples. So I'm going to do some examples, and again, there's going to be a video for you to watch. So I'm going to post the video on the example that I skipped, example 7, but there's also going to be more videos on conditional probabilities. So we'll do a couple, and then you guys will look at the video for the rest. Okay, let's see what it says here. In this example, we're going to draw a ball out of the bag and ask us to find these 4 probabilities over here. The thing is, when it comes to conditional probabilities, there's kind of 2 ways of thinking about them, depending on if you're drawing once or if you're drawing more than once. Okay, so if you're drawing once, think of it one way. If you're drawing more than once, think of it another way. Again, that's why I need you to watch the video as well, because I do some examples of drawing more than once. But in this problem, we're drawing once. Okay, let's go with this first one, probability A given B. Okay, so here's how you think about it. If I draw once, think about it like this. I want you to imagine I drew a ball out of here. I take it out. I don't look at it, but I show it to you. And when I show it to you, instead of you telling me what it is, you tell me this happened. Greg, you drew a ball that has a prime number on it. As soon as you told me it has a prime number on it, it can't be 10 anymore. You've eliminated that from being possible. It can't be 9, can't be 8, can't be 6. These are prime numbers. Can't be any of these anymore once you've given me that information. Okay, so the sample space, even though it has 10 things in it, once you tell me, hey, Greg, here's some information. It's got a prime number on it. You've eliminated some things from being possible. So I want to figure out what's still possible. So I'm going to call this the new sample space. Well, if you tell me it's prime, then it has to be the number 2, 3, 5, or 7. Those are only primes in the bag. So I guess what you do is you start off by figuring out what the new sample space is. And then you count how many things are in the new sample space, and that would be your denominator. Denominator is always how many things are in your sample space, but it's going to be how many things are in your new sample space, so 4. Okay, there's 4 things in the new sample space. So take the information that's given to you, figure out what the new sample space looks like. However many things are in the new sample space, put it on the bottom. Then, to figure out the top number, we're trying to find the probability of A. A is even. You have to count the evens. Now listen to what I'm saying. Don't count the evens here. Count the evens in your new sample space. Once you figure out your new sample space, forget the old one. Okay? Count how many evens are in the new one. How many even numbers in the new one?
1.
1. And that's the answer to that one. Okay, questions on that much? Let's make more room here. Okay, let's try the next one. Okay, so once again, when you draw once, think of it like this. Imagine I draw a ball out of the bag, I show you, but I don't look at it. And you tell me, Greg, A occurred. What'd you tell me? Greg, you drew an even. As soon as you told me I drew an even, the new sample space, these are what's still possible after I have the new information. The number must be 2, 4, 6, 8, or 10. So what's the bottom number going to be?
5.
5. Okay, cool. And then to figure out the top number, we're trying to find the probability of probability of B. B is prime. You have to count the prime numbers. Again, do not count the prime numbers here. Count the prime numbers in your new sample space. The only one that's prime in there is 2. So there's 1 prime number, put a 1 on top. That's that one. Let's try the next one. Okay, guys, you're going to help me out on this one, okay? So, again, I'm drawing once out of the bag. Think about it like this. I put my hand in the bag, I draw it, I show it to you, but I don't look at it. You tell me F happened. What'd you tell me? You drew a ball that is less than 7 and odd. Once you told me it's less than 7 and odd, what is still possible? Someone tell me, what's still possible?
5, 3, 1.
Yeah, 1, 3, 5. Less than 7 and odd. Once you give me that information, that's what's still possible. Imagine every other ball in the bag has disappeared. It's gone. So the bottom number is how many things are in your new sample space. So what's the bottom number?
3.
3. And again, for the rest of the problem, forget this sample space. This is the sample space we're working with. Now to get the top number, we're trying to find the probability of C. Let's read what C is. C is draw a yellow ball. Count the yellow balls. Don't count here. Count here. How many of the ones on the bottom there are yellow?
3.
There's 3. 3 is yellow. So 1 goes on top there. Sorry, they all have 1s on top. The next one will not have a 1 on top. Okay, let's try this one. So again, I draw one ball out of the bag, I show it to you, but I don't look at it, and you tell me E happened. So you said, Greg, just so you know, the ball you drew a ball with a number larger than 6 on it. Sorry, this got cut off a little bit. So the number is larger than 6 is what you told me. So here is what's possible after you told me that. What's possible? Tell me.
7, 8, and 9, and 10.
7, 8, 9, 10 are still possible, right? So denominator is how many things are in your new sample space? We got 4 things there. We start like that. And then the next thing is, I'm trying to find probability of A. So you have to count the even numbers. But again, don't count the even numbers in here. Count them in your new sample space over here. How many even numbers?
2.
2.
2.
That's how you do a conditional probability. So you don't really have to do any formulas, but you do have to understand it. Okay, see, and even you don't even have to write the new sample space if you don't want, but I'm writing it to make it a little easier on you, especially if it's a harder problem. You don't have to list the whole new sample space. Just figure out your new sample space and do the whole problem as if you're working with this new sample space. Okay, questions so far? Okay, then this question says, are the events A and C independent? So if you're going to check to see if events are independent, here's what you're going to do. You're going to write down a conditional probability. I'll leave spaces for now. And you're going to write down a regular probability here. So 2 spaces here, 1 space here. I'll put a question mark on equal sign. Now what you're going to do is you're going to put one of these events here, the other one goes there. It doesn't matter which one you write where. Let's say I put the A here and on the left of the line and C goes after the line. Then what has to go here? Whatever's on the left of this line has to go there. So A has to go there. Okay, so whatever's on the left of the line has to match what's by itself on the other side. They have to match. Okay, then you calculate them. Okay, so I'm going to calculate. Let's do this one first. Let me do the work over here. So again, I want to think about the new sample spaces. So one more time, I draw a ball out of this bag. I don't look at it, but I show you, and you tell me C happened. So you said, Greg, just so you know, it's yellow. So what's still possible after you've given me that information?
3 and 2.
1
Yeah.
and 2. I mean 2 and 3.
2 and 3 are still possible. That's it. So the bottom number for this probability is 2. You count how many things are in here, there's 2 things. Now to get the top number, you have to count A, which is count the evens. But again, don't count the evens up here, count them in here, in the new sample space. How many evens in the new sample space?
1 even.
Just 1.
Okay, look here at the new sample space, there's only 1 even number in there. Just the number 2. Okay, now to get the probability on the right side, this is not a conditional probability, it's a regular probability. So we're drawing out of this bag, so the bottom number is going to be 10, because it's, you know, the bottom is always how many things are in your sample space, but my sample space is this. It's not getting changed. It changes if you're doing a conditional probability. I'm trying to find the probability of getting an even, so you have to count the evens in the original sample space. How many?
5.
5, yeah. And now just check to see if those 2 fractions are equal. Are they equal?
Yes.
Yes. Now, sometimes it's not clear if they're equal. So if you're having trouble seeing if they're equal, then what you want to do is you want to divide the numbers on your calculator. Because it's possible fractions can look totally different, but be equal. But when you write them as a decimal, the only way they can be equal, they have to look identical. So you see they're equal. Since they're equal, you're going to say, so A and C are independent. And if they weren't equal, you'd say they're not independent, and that's the end of the story on example 8. And this time we're drawing more than one. So the experiment is we draw 2 balls from a bag, 1 by 1 with replacement. We're going to do a without replacement problem soon, but this one is with replacement. What does that mean? That means I draw the first one, put it back in, and then draw the second one. Now I know this part over here where I label what the events are might be a little confusing, but it's not a big deal. Basically what I'm asking you is to find, when we look at this first example here, I'm asking you to find what's the probability of the second one. So the number down here is telling you which time you're drawing. What's the probability the second ball you draw is red given that the first one is red. And then same thing for the other one. So this would be the second ball is green, given the first ball you draw is red. Okay, so the number underneath the letter just tells you which draw you're on. Is it the first draw or the second draw? When you're drawing from a bag once versus more than once, and you're trying to find conditional probabilities, I want you to think of them way differently. In class, we said that when you draw once, I said think about it like this. Imagine I draw the ball out of the bag. I show you, but I don't look at it, and you give me information. But this time, since we're drawing more than once, I want you to think about it a little differently. So think about it like this. I want you to imagine that this has occurred. The event after the vertical line has occurred. And I'm about to draw the second time. So I've drawn the first one, I'm about to draw for the second time. So what's happened the first time? I've drawn a red one. Okay, that's what it means. So the first ball I drew was red. And then we're about to draw the second time, but when you go to draw the second time, you have to think, how does the sample space change? And the answer is it doesn't change. Sample space doesn't change. Let me write that down. Sample space doesn't change. Why? Because after you draw the first ball, it's red. You put it back in before you draw again. So when you're about to draw the second time, the sample space looks exactly like this. All the balls are in there. Okay, so the probability the second one is red is the probability I get a red one if I was to draw one time from this. And the answer, bottom number would be 10 and top number is 1. Let me say it one more time. So this has already occurred. Let me change the color here. This has already occurred. That means I've drawn the first ball out of the bag and it was red. Then I put it back in and I'm about to draw the second time. When I go to draw the second time, now I want to know what's the probability that I get a red one so that the second draw is red. And well, what does the sample space look like? It still looks just exactly like this. So what's the probability I get a red out of here? 1 out of 10. This example 5, the problems are kind of too easy. It's a little more interesting when you go to example 6, but I had to put a couple like this anyway, so let's do one more like this. Okay, so again, when you're drawing more than once, I want you to pretend the first draw has already occurred, so this has already occurred, and I want to know what's the probability that I get this on the second draw. So just like the last problem, the idea is the first ball I drew was blue. Okay, that's great, but then we put it back in since we're drawing with replacement before we go to draw the second one. So when I go draw the second one, what does the sample space look like? The new S is the same as the old S. It's this. Nothing has changed because after we draw the first ball, we put it right back in. So I put it back in. Imagine I've drawn the first one, I put it back in, and I'm about to draw again. What's the probability I get a green? And the answer is 3 greens, 10 total. Yeah, that's it for that one. Okay, I know it's a little too easy, but you'll understand the difference when we get to example 6. Okay, we got one more question. Are the events R2 and B1 independent? Okay, there's two ways to do this problem. One way to do it is to just say, yes, they're independent because we're drawing with replacement. So let's write that down. So yes, because we're drawing with replacement. Okay, so with replacements, they're always going to be independent. Any two events you give me, they're going to be independent. Okay, so that's one way to say it. And that's fine. I'll take that answer if that's what you write. But let me go ahead and try to write it another way. Let me go ahead and erase this real quick. Okay, so another way to do it is with the formula for independence. So how would it go? So we're going to do a conditional probability here and a regular probability here, and I want to know if they're equal. So you're going to put one of these events, R2 or B1, here in the first slot and B1 and the other one in the second slot. It doesn't matter which one you put where. I'm going to go ahead and put the R2 here. I'm going to go ahead and put the B1 here. So we're going to do R2 given B1. But then once you've determined what goes there, you have only one choice for this. Okay, so one choice. And what is it going to be? It's going to be R2, whatever you have written before the vertical line there. Okay, so over here we're going to put R2. And what you can do is you're going to calculate these two probabilities. And if they're equal, then the events are independent. Okay, so let's see what they are. let's start with the one on the left. Okay, so this one here. Again, the story is B1 has already occurred, and I'm about to draw a second time. So again, when you're drawing more than once, think about it like this. The event after the vertical line has occurred. That means you've drawn the first one. It's blue. And you're about to draw the second one. So you haven't drawn the second one yet, but you're about to. I don't want to know what's the probability the second one is red. And remember that if this has occurred, the first one's blue, it came out of the bag, but then it goes back in before you draw the second one. So when you go to draw the second one, what happens to the sample space? Sample space stays just like this. So since it stays just like that, what's the probability the second one's red? Well, we've got 1 red, 10 total in the bag. That's how that one goes. Okay, and then the second question, or the second probability here says, what's the probability you draw red the second time? And irrelevant of what happened the first time, and you already realized that it is irrelevant what happened the first time anyway, because you put it back in. This is also 1 out of 10. You can see they're equal. So they are equal, so R2 and B1 are independent. Some of that might have been so easy that it's confusing, and again, I get that. But you'll see how it changes completely when we get to example 6. All right, let's look at that now. Okay, so once again, we're drawing 2 balls out of the bag, but this time it's without replacements. So things get more interesting here. And again, I'm asking you to find all these conditional probabilities. So let's go ahead and find the first one. This one says, what's the probability the second ball you draw is red given the first one you draw is red? Okay, so again, remember how we're going to think about this when you draw more than once. This has occurred. That means the first ball we drew was red. And I now want to know if I go to draw the second time, what's the probability the second one is red? So where are we in the process of drawing? The first one's been drawn, and we're about to draw again. Okay, so you need to think of what the new sample space looks like. Okay, so if the first one is red, so if the first ball we drew is red, we're drawing without replacement. That means once we've drawn it, it stays out. We don't put it back in. So if we don't put it back in, then what does the new sample space look like? Well, this says the first one was red. That happened. And it's out of the bag. So it's kind of like this one is gone. And now I'm about to draw from this new bag here. Okay, so this is my new sample space right here, everything else. Okay, so if that's my sample space, what's the probability the second one, the one I'm about to draw, is red? Well, there's no reds left. So it's going to be 0 out of what? Well, how many things are there total? 9. 0 out of 9, which is 0. That should make sense. If the first one was drawn red, what's the probability you get a red again? You can't because there was only 1 red and it's already been taken out, not going back in, so the probability is 0. So again, did you see how the sample space got changed? In the last problem, it didn't get changed because we put the ball right back in, so we're drawing from the same exact bag again. But this time, one of the balls is out and not coming back in, so the sample space went from 10 things to 9 things. All right, let's go ahead and look at the next one. Okay, so again, whatever's after the vertical line has occurred. So think of it like this. We've drawn the first ball, and we're about to draw the second one. So we've drawn the first one, it's blue. It's out of the bag, and it's staying out. And I'm about to draw the second one, what's the probability the second one is green? Okay, before I figure out this answer, I want to think of what the new sample space would look like. So I've already drawn the first ball, it was blue. And it's out of the bag and it's staying out. So we got to take a blue one out of the bag. Just take any one that's blue. I guess it doesn't really matter what the number is. Let's go ahead and just cross off this one. That one is out of the bag and it's staying out. And now I'm drawing from this new bag that has 9 balls in it instead of 10. What's the probability I now get a green? Okay, so once you realize what the new sample space looks like, should not be a problem. Bottom number is going to be 9 because again there's 9 things in there. And how many of them are green? 3. So that's just 3 out of 9. You could simplify that if you want, or write as a decimal or something. It's up to you. Okay, let's try the next one. Okay, so this says find the probability that the second ball you draw is blue given that the first ball you drew was blue. Once again, where are we? We've drawn the first one. It was blue. This happened, so it was blue, and it's out of the bag, and we're about to draw the second time. And I want to know, just before I draw the second one, what's the probability I'll get a blue one? So you again have to think, what is the sample space going to look like? Well, we've drawn a blue, and it's out of the bag, and it's staying out. So again, you could just take one of the blues and cross it out, because it's been taken out of the bag. Let's just go ahead and cross out this one, for example. Doesn't matter. And everything else now is my new bag, new sample space that has 9 things in it now. And if I draw from this new bag, what's the probability I get a blue? I want to know what is the probability I get a blue. All right, so fraction line, bottom number, 9, because there's 9 things in my new sample space. And how many of those are blue? 3. So answer is 3 out of 9. Once again, simplify if you want, it's up to you. But I'm worried about this example. Some people might write 4 because there were 4 blue ones, but remember we removed 1. So the new sample space doesn't have 4 anymore, it has 3. Okay, so 3 blues left, 9 total left. Okay, let's try the next one. Okay, so this problem is asking, what's the probability the second ball you draw is red given the first ball you drew is yellow? One more time, let me say where we are in the drawing process. We're about to draw the second one. We've drawn the first, we're about to draw the second one. A little more. We've drawn the first one and it's yellow. It's out of the bag and it's staying out. And now I want to know what's the probability the next one is red. So the first thing you do is you figure out what your new sample space is going to look like. If the first one has been drawn and it's yellow and it's out of the bag and it's staying out, then I'm just going to go take a yellow one and cross it out of the bag and see what's left in the bag. Let's go ahead and cross off the 2, for example. It doesn't matter. Any yellow one is fine. So imagine this one is the one that was drawn out and it's gone. It's not coming back in the bag. And now I'm drawing from this new sample space right here. And from this new sample space, what's the probability I get a red? That's the question. Okay, so fraction line. The bottom is going to be 9 because there's 9 things total in the bag. And how many of them are red? 1 red. So that's the answer to that, 1 out of 9. All right, that's how that goes. Okay, a couple more examples. Let's go ahead and look at example 7. Okay. In this example, the experiment's changing. Now we're drawing a card from a poker deck. We're drawing 1 card from a poker deck. And it's asking to find a few conditional probabilities. We're drawing 1, so it's going to go back to the ideas we talked about in class. So when you draw 1 versus when you draw more than 1, remember, you're going to think about conditional probabilities in a little bit of a different way. So when we're drawing more than 1, I told you have to imagine you're at the point to where you're about to draw the second. You've drawn the first already, you're about to draw the second. When you draw only 1, what I want you to think about is that you've drawn it, but you're not looking at it. And someone else is going to give you information about it. Okay, so let's go ahead and look at these examples here. Okay, so in this problem, they're asking you to find the probability of C given A. C is that you get a red face card, and A is that you draw a heart. So I want to think of what happens to the sample space. I'm only drawing 1, so imagine I have a deck of cards. I draw 1 card, I don't look at it, but I show you. And you tell me that A occurred. That means you tell me I drew a heart. As soon as you told me that I drew a heart, we have a new sample space. The new sample space is all the hearts. Ace hearts, 2 hearts. Since I'm running out of room, let me just go ahead and write it like this, King of hearts. Once you told me that I drew a heart, it has to be one of these cards. Can't be anything else. So I automatically know that my sample space that I'm drawing from has 13 things total, so that's what goes on the bottom. And now I want to know what the probability is to get a red face card. So what you want to do is you want to count the red face cards. Red face cards that are in here. Okay, that's my whole sample space. Forget about any other cards besides those. And well, all those cards are red. That's good. They're all hearts. How many red face cards are there in this group here? The answer is there's 3. Jack of hearts, Queen of hearts, King of hearts are in there. So 3 goes on top. So that's the answer to that one, 3 out of 13. Okay, so let me say it one more time. So we drew 1 card. I show you. You tell me it's a heart. So now I know there's only 1 of 13 options it could be. That's why 13 goes on the bottom. Now I want to find the probability that the card is a red face card. So of those 13 in my new sample space, how many of them are red face cards? And there's 3. I didn't list them all here, but it was Jack, Queen, and King of hearts. Don't put Jack, Queen, and King of diamonds because they're not in my new sample space. Okay, let's try another one. Okay, this time they're asking to find the probability of B given D. We're only drawing 1, so the way you're going to think about it when you're drawing 1 is like this. So imagine I've drawn 1, I show it to you, but I don't look at it, but I show it to you, and you tell me that D occurred. That means you told me I drew a king. Okay, so this has occurred. I drew a king. Okay. And then I want to find the probability that it's a black card. Okay, so this is the one I'm trying to find the probability of. Okay. So because you told me it was a king, it can't be any of the 52 cards. It can only be one of the 4 kings. So the new sample space is now the king of clubs, king of diamonds, king of hearts, and king of spades. Has to be a king, and there's only 4 kings in the deck. So that's my new sample space, so don't think about any other cards for the rest of this problem besides those kings. So the bottom number is 4 then, because there's 4 things in there total. And now I want to know how many in here are B, whatever B says, black. So how many of these are black? And the answer is 2 of them. King of spades, king of clubs. So 2 out of 4. If you tell me that I drew a king, there's only 1 of 4 options. If I want to know what's the probability now that I have a black card, well, of the 4 options, 2 of them are black. So 2 out of 4. All right, let's try the next one. All right, same thing. We're drawing 1 card from a deck. It says find the probability of D given C. So again, I've drawn 1 card. It's already been drawn. I'm not going to draw a second one or anything, but I don't look at it and I show it to you. You tell me that C has occurred. You tell me it's a red face card. As soon as you tell me that, I know what my new sample space is. I know it's got to be a red face card. So it's a jack of hearts, queen of hearts, king of hearts. Those are the heart red face cards. And then the jack of diamonds, queen of diamonds, king of diamonds. Those are all the red face cards. So I know for sure the bottom number is 6. Okay, so now I want to find the probability of D given this new information. I want to know the probability of drawing a king. Don't count all the kings, only count the kings that are in here because my old sample space is gone. It's just this new sample space. And in my new sample space, there's 2 kings, so 2 goes on top. And the answer is 2 out of 6 for that one. Okay, let's see what the question is over here. Okay, so the question is, are the events A and D independent? So the way we're going to do that is we're going to set up 2 probabilities. So I'm going to put a conditional probability here, and put a regular probability here. In the first probability, you're going to put A somewhere, and you're going to put D somewhere. Let me go and put the A first and the D second. You can put the D first and the A second. I think I'll do it that way as well, so you can see what happens. But put one of them first, put one of them second. Once you've decided which one goes first, which one goes second, on the right side here, you have to put whatever you wrote first. So it has to be an A here. If you put a D there, it's not going to work. Okay, so whatever's first here has to match what's in here. Okay, so now we're going to calculate those numbers. If those numbers are the same number, those events are independent. If they're different numbers, the events are not independent. Okay, so let's start with the conditional probability. For the conditional probability, D has occurred. That means I drew the card, I didn't look at it, I showed you, and you said I drew a king. That means the new sample space are the kings. So king of clubs, king of diamonds, king of hearts, king of spades. So there's 4 things in the new sample space. Okay, then I want to know the probability of A. Okay, so I want to know the probability of getting a heart. So I want to count the hearts in here, and that's pretty easy. There's just 1 heart there. So that is 1 out of 4. Now what about probability of A? This is not a conditional probability. So just find the probability of drawing a heart out of an entire 52 deck card, deck of cards. 52 card deck is what I meant to say. So 52 down here. And how many of them are hearts? 13. Turns out those are equal. If it's not obvious, put in the calculator, write as a decimal, you get 0.25 here, and you get 0.25 here. So they are equal. So A and D are independent. Yeah, that's how that one goes. Okay, I'm going to do this one more time where I just switch the order of the 2 terms that are in the conditional probability. So let me go ahead and erase this real quick. All right. So once again, to find if they're independent, I'm going to put 2 probabilities. This one here is going to be a conditional probability, and this is going to be a regular probability. But this time I'm going to put the D here and the A here. Remember, it doesn't matter which one you put where. So I'm going to put the D first and the A there. But if I do it that way, then on this side, what do I have to put here? The answer is I have to put D there. I have to put whatever it says first there. It's going to be a D. I'm expecting the same answer because in the last way we did it, we said that it was independent. So I'm expecting these two numbers to be the same so that I get independent again. And that's what will happen. Let's go ahead and look at this. So for the conditional probability, remember A has occurred. That means you told me, think about it like this. I've drawn one card from a deck and I show you, but I don't look at it and you tell me it's a heart. And that tells me now my new sample space is all the hearts. Ace of hearts, two of hearts, all the way up to Jack of hearts, Queen of hearts, King of hearts. All the hearts. So that new sample space has 13 things in it, so the denominator for this is 13. But then I want to know the probability of D, the probability I draw a king from this new sample space. There's only one king in the entire new sample space, so 1 out of 13 for that. Okay, and then the right side, probability of D, what's the probability I draw a king? This is not a conditional probability. It's out of the entire deck. What's the probability I get a king? The bottom number is going to be 52. And how many kings do you have in the deck? 4. So 4 out of 52. Those are equal. If you don't believe me, then you put them in a calculator. Now, of course, I have to find a calculator around here. So let's see, 1 divided by 13, and I'm getting 0.076923, anyway, more digits than that. And 4 divided by 52, of course, same thing, 0.076923. They are indeed equal. So what does that mean? So A and D are independent. Yeah, that's how that one goes. Okay, let's look at example 8. Okay, a detective is trying to solve a murder case. At the outset of his investigation, he knows that the murderer is one of the 200 people in the following table. So apparently the murderer is either male or female, and either from Montebello or Pico Rivera. I made the table red, incidentally, just so you can get in the mood, the murder mystery mood. Okay, so then we have 3 questions. The first one is, what is the probability that at the outset of the investigation, the murderer is female? Suppose that after further narrowing down the suspects, the investigator has determined that the murderer lives in Pico Rivera. Now what is the probability that the murderer is female? I hope that you can see the distinction between A and B. A is just a regular probability. B is a conditional probability. We have further information, and then asks you to find the probability of the same thing. First one says just probably the murder is female. Second one is, given this new information, what's the probability the murder is female? So B is a conditional probability. And then for part C, it says, are the events murder is female and murder lives in Pico Rivera independent? All right, so look, there's no letters for events mentioned in this question. So the first thing you want to do is you want to make up letters for the different events. There's only 2 events mentioned. One of them is that the murderer is female. So we'll use F for that event. And murder lives in Pico Rivera is the other event. So I think I'll use PR for Pico Rivera for that one. Okay, let's go ahead and write that down first. Okay, so F is going to be the event that the murderer is female. And we'll use PR for the event that the murderer is from Pico Rivera. Okay, let me make this F a little nicer looking. Still can't make it nice. Okay, that's better. All right, so for the rest of this problem, F is going to stand for the event that the murderer is female, and PR is going to stand for the event that the murderer is from Pico Rivera. Okay, so let's go ahead and answer the questions. Part A, what is the probability that at the outset of the investigation, the murderer is female? Okay, so I'm going to write down the notation for the question first. The mathematical notation for this is just probability that the murderer is female. Okay, it's pretty easy here. You just put a fraction line. We can use absolute value, the classical formula that involves absolute values. It's absolute value of F divided by absolute value of S and I just count. How many females are there total? Right here, females total 60. 60 goes on top. And how many people total in the entire table? 200. So 60 over 200. Okay, that one was easy enough. The second part is a conditional probability. So suppose after further narrowing down the suspects, the investigator has determined that the murderer is from Pico Rivera. Now what's the probability the murderer is female? The notation now is I want to find the probability the murderer is female, so F goes first. Given the new information, and that new information is that the murderer lives in Pico Rivera. Okay, so once you told me the murderer lives in Pico Rivera, it narrows down my sample space. At the outset of the problem, the sample space was all the people in this table. But it's not anymore because now I have this information, the murderers from Pico Rivera. So my new sample space just gets cut down to the people from Pico Rivera. So everything that's in this green box here, that's my new sample space now. You can ignore all the people that are outside of it. Basically ignore all the Montebello people. Let me do a little bit of erasing here. Okay, so now to get the answer, we're going to put a fraction line here. Well, in my new sample space, how many people are there total? In my new, here's where it says total, so 50 people total in my new sample space, so 50 down here. Okay, and of those, how many are female? So this is the female column right here. So how many female? 15. So that's the conditional probability. Again, you don't go anywhere outside this Pico Rivera column right here. Okay, so that's how that one goes. Again, if you want to simplify it, it's up to you. So this last part says, are the events murder's female and murderer lives in Pico Rivera independent? Okay, so to check for independence, we're going to go like this. We're going to do a conditional probability first. Probability, conditional probability, and then regular probability here. Okay, so what am I going to put things? So I'm going to put female either here or here. And I'm going to put Pico Rivera either here or here. So it doesn't matter, but put one of them first, put one of them second. And I'm going to go ahead and put female first and Pico Rivera second because we already found that one. So let me go ahead and erase this now. Oops. Okay, so I'll put female here, Pico Rivera here. Then this one has to be female. And of course, we already found all these. So let me go ahead and just put these answers here real quick. So part A was the right side, probably murder's female, which was 60 out of 200. And the right side was part B, probably murder's female given they're from Pico Rivera, was 15 out of 50. And again, if you can't tell if those are equal or not, you put them in the calculator, do it as a decimal, and you're going to get 0.3 here, and you're going to get 0.3 here. Okay, so I wanted to know if they're equal. Now I know. So what's the conclusion? So since I'm running out of room here, let me just go ahead and use the symbols. Murder is female, and murders from Pico Rivera are independent. They are. Yeah. That's how that one goes. Okay, guys, so practice a lot more conditional probabilities.